And welcome back to another Math 1 homework helper. This is going to be for Unit 3, Lesson 5 for Math 1. Let's get into it. So right off the bat, we're asked use the graph of each function to determine the indicated values. I did an entire piece on this in the last episode about how you go about finding these. It's really saying, all right, you're given an x, go find the corresponding y that sits on that graph, or you're given a y and have to find the x. So in this case, I'll do a bunch of erasing here just to kind of show up. In this case, it says f of 4 is equal to what? So it's saying when x is 4, what's the corresponding y? So we say when x is 4, go up. What is that y value? We know that that ends up being 1. Cool. We'll get rid of that. We get f is negative 4. So we just say, all right, when it's all the way out here, when x is negative 4, what's my corresponding y value? In this case, we get that it's 7. It changes a little bit in problems C and D, nothing crazy, but it does say, all right, when f of x is equal to 4, find what x is. So we're saying when y is equal to 4, oh, well, we're sitting right on our function already. So we know that this has an x value of 0 because we didn't have to go anywhere to ignore it. We'll switch back to orange here, so I apologize. We're saying when y is equal to 7. So we go up to where 7 is. We go, all right, well, there's 7. We come across, and then what is the corresponding x value? We get that that's negative 4, which we actually knew because we had just done that in problem B, just the reverse order. But if you didn't see that, that's how you go about solving that. Now, we look at g of x here. All we have is an exponential. That's all the difference here. So still doing the same thing. We're looking for, all right, g of negative 1 when x is negative 1. Oh, maybe. When x is negative 1, what's this corresponding y value? We get that that is negative 2. Let me erase that. We then say, all right, when x is negative 3. Well, that one looks awfully close. That one's going to be a little bit tougher for us to do, just so we know what negative 2, negative 4, it's going to be negative 8. Just from looking at it and seeing that we have a, it's doubling by negative 2 every time we get lower to get there. Cool. Yeah, that's a pain in the butt one. We then get g of x is equal to negative 4. We're saying when y is negative 4. What's this? Oh, it's going to be equal to negative 2. And our last one, we'll jump back into orange, is when when y is negative 1. So that's here. What's our x value? Well, that's just going to be 0. Get there. Awesome. So not a whole lot of different. That's very familiar stuff from what we did last class. But we're going to keep going. So we then move into problem number 4, which is this whole piece here, where we're doing the same thing, except that we're broken up and we might have multiple solutions given where things are sitting. So when it's asking when x is negative 5, it's saying, all right, I'm going to draw a line at negative 5. That's right there. Let me change that color though. I really don't like that. That doesn't pop more. We'll go back to bright pink. So we're looking for how many times, what are the y values when this hits? And it's only one time, and that's when y is equal to, when x is negative 5, our y value for that is positive 1. We're going to reset. We're going to say, all right, well, what happens when x is equal to 4? And we go through and we say, all right, let's draw our line. How many times do we end up hitting there? Once, okay, what's our y value at that point? And we say, oh, that's at positive 2. Because we're just saying, what's the y value at that point? 4, negative 2. All right, we'll reset again. Here's where it gets a little bit different. We'll even change the green for this one. It's asking when y is equal to 4. 1, 2, 3, 4. We go straight across. How many times do we hit? Only once, and that's when x is equal to positive 3. Oh, that didn't work. And our last piece of this, once again, I'm going to erase that green line, is going to go through and say, all right, well, when y is equal to 0? Well, when y is equal to 0, we go through, and how many solutions do we have? How many times does our graph end up hitting this? And the answer is 4. I'm looking at 1, 2, 3, and 4. So we have to list off every x value for that. And I'm just going to start left to right. We're going -6, 0, 1, and 5. So we can get multiple of the same answers with some of these. We just have to make sure we're not stopping as soon as we find one. Just make sure you're going all the way across or all the way up and down to make sure that there aren't multiple correct answers. Awesome. So then we're going to move in over here to 5. For the rest of this, I think it's a lot more of me just talking and you guys paying attention and listening to it, just because you guys know that I don't like writing down all the everything in English. I'll do the numbers out for you, but I'm not going to waste your time writing it out when I can just talk you through it. So for this problem, it says for each situation, either create a function or use the given function to find and interpret solutions. We're going to more lean towards the interpret solutions piece with this. But the question is, or prompt is, Fran collected data on the number of feet she could walk each second and wrote the following rule to model her walking rate. She got d of t, which is just f of x. Just think of it that way. F of x is equal to 4x, or d of t is equal to 4t. The reason she chose d and t is because t is her time and d is going to be distance. So, for every second that she walks, she goes 4 feet. That's what that function said, which I may have just gone through and said. But what it says here is, what is Fran looking, this is part A. What is Fran looking for if she writes d of 12 is equal to blank? What she's looking for here is she's trying to figure out how many feet she walked in 12 seconds. So you just plug 12 in for t there and solve and get that that's 48 feet in 12 seconds. In part B, it's asking, in this situation, what does d of t equaling 100 tell you? What that's telling you is it's asking her how long did it take her to walk 100 feet? And so we could go through and solve that and say, all right, well, we put in 100 there and we try to solve, for what that time is going to be. So that becomes 100 equals 4t. You could divide by 4 and it would be in 25 seconds, t is equal to 25. So 25 seconds, she's going to walk 100 feet. Part C is, how can the function rule be used to indicate indicate that a time of 12 seconds was walked? If she went through and she plugged in 16 for t, so she got d of 16 is equal to 4t, she could go through and say, how many feet did she walk in 16 seconds? How can the function rule be used to indicate that a distance of 200 feet was walked? So very similar to part B, we go through and say d of t is equal to 200. So when we build the equation, it's going to be 200 equals 4t. And we can go through and do the math and divide by 4 and get that t is equal to 50. So in order to walk 200 feet, it would take her 50 seconds to do so. Cool. So like I said, that's me just kind of talking through that problem instead of writing it all down, but you feel free to back up, pause it, whatever it is that you end up needing to do. Problem 7, very similar to this, is that Hope has been tracking the progress of her family as they travel across the country. She knows that they are driving 78 miles per hour during vacation, and she has created a function, d of t is equal to 78t, to model the progress they're making. So just like the last problem, we're using d of t for distance, how far has she gone, and t as time. However, in this case, in this problem, they're dealing with time as in hours, not in seconds like it was in the previous problem. So when it goes through and says, sorry, make sure I'm on the right stuff. What would Hope be attempting to find if she writes d of 4 is equal to 78 of 4? Her hope is to say, how far have they gone in 4 hours? How many miles have they gone in 4 hours? Part B is, what would the expression d of t equals 450 mean in this situation? All that's asking is that if they've driven 450 miles, how many hours have they driven for? So they're just saying 450 is equal to 78t, and then go through and solve. Part C, what would the expression d of 3.5 mean in this situation? That is, how many miles has she and her family gone in 3.5 hours? Just go through, plug in 3.5 in for t, do 3.5 times 78, and you're going to get the distance that they've gone. And then part D, how could Hope use the function to find the time it would take to travel 800 miles? So she goes through and does this. That means that d of t is equal to 800. So she's going to set up that equation as 800 is equal to 78t. Just divide both sides by 78, and you're going to get the amount of hours it's taken to drive 800 miles. Cool. And then there's problem 8. Problem 8, which I am going to do not talk you through, so I apologize for that. Which is we've got two functions. We've got f of x and then we've got g of x. Just for the sake of everything, we'll go through and say that we've got g of x is our exponential, and f of x is our linear. So pink. What we're looking for here is it's asking where is f of x equal to g of x? And what we're looking for is we're saying, okay, what are the x values where they have the same y values? And so we look for those points of intersection. We've got one up there and one up there. But we have to say, what are those x values that give us the same y values? So we're just looking at that left one. It looks like it's -5, 6, 7, 8 at -8. And at 0. Oh, those aren't points. If we had a right amount, that would be -8, 5, and 0, -4. If we were looking for one of those intersection points. So either way, you could get away with right ones. When we're looking at part B, it's saying when x is 0 in function g, so let's go to green, we're saying, all right, we go down, and that ends up being -4. So come on. That ends up being equal to -4. Then we're going to say plus, and we're going to look and say here, h of 0, I'll try to color code these here, is that when f is 0, or I'm sorry, in f of x, when x is 0, we're going to get the same thing. It just happens to be one of their intersection points where they're both at 0, -4. And then we go through and say -4 plus a -4. This is going to give us -8. That's not a point. That's just saying, hey, this function plus this function, what's the outcome going to end up being? For the next piece, for problem C, it's saying on what intervals is g of x greater than f of x? It's saying when are the y values of green greater than the y values of pink? And for me, I'm seeing that in two different spots. Let me see if I can get rid of this. I'm seeing that once we get past here and once we get past here. Because if I move to the right over here, green is higher than pink, green is higher than pink. But we need to write that in interval notation. So when we do that, we're going to end up saying, we always move from left to right. We're saying anywhere from -infinity. Oh, that could have been bad. Yikes, don't do that. We're saying -infinity until we reach what is that x value, that's -9. We're going through and saying, here's the thing though, we're going to say in parentheses, because once we hit 9, they're equal, and therefore g of x is not greater than f of x. So we've got to say that that's not true. And we also have, where else does it get larger? It's when we get to 0 to positive infinity. And the same thing, we're going to leave those as open sets of parentheses because they're not, neither one's greater than the other when they are equal to each other. So we leave it as that. For this last one, it is saying, all right, when we've got all sorts of stuff written on there, so I apologize. Let's go get a color we haven't used. Let's go light blue. When g of x is, or g of -8 plus f of -8. So we're looking for what g, our green function, is 5, 6, 7, 8. I got to get rid of some of this mumbo jumbo in here. There we go. So it's saying, all right, at that point, and then, great. So these are going to end up being the same. What's the y value there? Oops. At that point, that y value for both of them is going to be 5. So 5 plus 5 is going to end up being equal to 10. So that's kind of difficult to show here on there, but remember, both of these, when x is equal to -8, both of their corresponding y values are going to be 5. So we're looking at 5 plus 5, which is that baby blue dot. And then we just get to go through and add those together to get 10. And just like problem B, that has nothing to do with any points or anything. So we get to just write that as one number. The rest of these, I believe I will be just talking through, and I mean it this time, for each context or representation, determine whether it's discrete or continuous or could be modeled best in a discrete or continuous way. Justify your answer. So in problem 9, Susan puts exactly $5 in her piggy bank every week. I would absolutely say that this is discrete. End of the week, she puts in $5. Boop, $5 richer, $5 richer, $5 richer. She's not continuously growing it with interest or anything like that. She is just discrete because she's doing it once a week and then it's all done. Problem 12. We have 3 more. Problem 12. Marshall tracks the number of hits he gets on a baseball game and records his total number of hits for the season in a table. I said that this one was discrete as well. You can't get hits outside of a game. You also can't get partial hits. I can't say, oh, I had 4.5 hits today. If you get a foul balls don't count in baseball or softball. So let's just avoid that. Discrete. You're getting a total number of hits, and it's got to be a whole number. Simple as that. 13, the distance you have traveled since the day began. You are continuously moving. I'm going to say that this is continuous. It tracks throughout the trip, throughout the day. That if even I'm just walking around campus, every step I take is going through and moving. I don't randomly teleport from here to being 3 feet this direction. Just not going to happen. So that is continuous because we can measure the distance that we have gone. And then our last one here. I think it's this gumball one. Yeah, so we're looking at problem 14, number of gumballs and their cost. When we look at this, for every 5 gumballs, we're going up 10 cents. That's going to be discrete. You're not able to go through and buy a fraction of a gumball or something like that. You're not going to go up and say, hey, I'd like 2 3/4 of a gumball, and they're not going to do that type of pricing. It's very discrete. You pay your 10 cents, you get 5 gumballs. Boop. You pay 10 cents, you get 5 more gumballs. Boom, 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 so on and so on and so on. So that is the end of another Math 1 homework helper. If you had questions on this, please go and see your teacher later this week. Have a great day.